This week's homework is about confidence intervals and hypothesis tests for two population proportions, and the calculator operations we're going to be using are 2prop z int and 2prop z test. The concept of a p-value is not really something that's easy to grasp the first time that you see it. So let's take a minute here to go over the definition one more time. I've set up a null and alternative hypothesis, and you can see that the alternative hypothesis is that p is not equal to p0. We're calling these two-tailed alternative hypotheses. The null hypothesis gets the benefit of the doubt, so I put p0 here in the middle of the distribution of all of the samples. So this is going to be a number in your problem. If the sample data comes in this range, then it makes H0 look true because we're getting results that are close to P0. However, if P hat comes in this range, then it makes P0 look not true because we're getting a result that's very far from what's expected. There are two possible explanations for why P hat is coming in different than what we expected. One is because of random chance, and the other one is because perhaps the null hypothesis is not true. So someone could always defend the null hypothesis by saying that our results disagree with the null hypothesis because of random chance. When that chance gets too small, that's when we reject the null hypothesis. If we assume the null hypothesis is true, then the farther p hat gets away from p0, the less likely it is that that's because of random chance. The p-value is the probability of getting a result that is as extreme as p hat or more extreme than p hat, assuming that the null hypothesis is true. So in this example, the alternative hypothesis is that we are assuming that there is a difference. So the null hypothesis is assuming that there is no difference. We're going to use the letter alpha here. It's the Greek letter A to represent the level of significance. When the p-value comes in less than the level of significance, that's when we do have enough evidence to reject the null hypothesis. Remember that p-values being small happen when z-scores are large. I used to share my office with another math teacher at JCCC, and she told me that eating locally grown honey would improve your allergy symptoms if you were allergic to pollen. So I built a statistics example based off this. So there was a double-blind experiment conducted, and there's 850 allergy sufferers that did eat locally grown honey, and then there were 800 individuals that were put in a placebo group, so they just ate honey that was sourced from far away. It may not necessarily have been locally grown. So before we jump into conducting any kind of fancy statistical inference here, let's just look at the two sample proportions that we got and see if that actually makes it look like the locally grown honey is making any kind of difference at all. So I let P1 be the treatment group and P2 be the placebo group, and boy, does it ever look like this is working. 77% of the locally grown honey eaters saw an improvement in their allergies, while only 60% of the regular honey eaters saw an improvement in their allergies. So just on our first inspection here, it really makes it look like the locally grown honey is making a difference. What we're actually estimating here is the difference between these two proportions. So that's where this D comes from. P hat sub D, D for difference, is 17%, because that's the difference between 77% and 60%. So we're asked to construct a confidence interval. And very clearly there are two proportions in this problem. One way that it's easy to identify that is because it's talking about the difference between two things. And also, if you just read the problem, you can see that I really have two proportions here. 653 out of 800 and 653 out of 850 and 482 out of 800. So they really are giving me two proportions. So I push the stats button and I right arrowed over to tests, and then you can see my calculator inputs here. So what this means is that we're 95% confident that the difference in proportions, the true difference in proportions, is somewhere between 12% and 21%. I want to be clear that this is the difference in population proportions. I don't need to make predictions about what the difference in sample proportions is. I know that the difference in sample proportions is exactly 17%, so I don't need any fancy statistical inference to tell me that. What I need fancy statistical inference for is to tell me what this means about the population. Really what we want to know is 0 in this interval? Because if 0 is in the interval, then it's plausible that the difference between these two proportions is 0. And what does that mean? If the difference between two proportions is 0, that means that it's plausible that these two proportions are the same. So is 0 in this interval? So no, 0 is not in this interval. So this example here is making it look like the locally grown honey is helping with people's allergies. I really have no idea if this is true in real life. I just 100% made up all these numbers. So don't go like eating a bunch of honey if you have allergies. In this example, we're going to be working out a problem about classical music and whether or not it helps you pass a statistics test. So this behavioral psychology professor, double-blind, placebo-controlled, randomized, blah, blah, blah. Anyways, the important thing is that 200 students listens to classical music and 162 of them passed. And then 138 of the 190 students that listened to heavy metal passed. So we're going to test the hypothesis that classical music students have a higher pass rate, and we're going to use alpha, the level of significance, as 5%. The first step in hypothesis testing is always to write the null and alternative hypothesis. I've given the benefit of the doubt here to the concept that it doesn't matter what kind of music you listen to, you have the same chances of passing the test if there's classical music playing in the background or if there's heavy metal music playing in the background. So the benefit of the doubt is going to go to the idea that there is no difference between these two proportions. So P1 equals P2. What we're testing is if the classical pass rate is higher than the heavy metal pass rate. So that would mean that P1 is bigger than P2. Here's the calculator input that I put in for my 2-prop Z test. These are just the numbers that came out of the problem, but I especially want to draw your attention to this right here. We were testing that the classical music students have a higher pass rate. And that led me to P1 is greater than P2. Then in the calculator, I have P1 is greater than P2. So just make sure that your calculator buttons are consistent with your hypotheses. Now we have to decide if we're going to reject the null hypothesis. So our kind of rule for doing that is the p-value less than the level of significance? So this time we got a p-value of about 0.02, and the level of significance that we're using is 0.05. So yes, the p-value is less than the level of significance. Here's everybody's favorite part, writing the technical conclusion in the context of the problem. So this time we did reject the null hypothesis, so we do have significant evidence. I think one of the hard parts for students is actually reading comprehension and trying to understand the context of the problem. In this situation, what we're concerned with is the pass rate of these two populations of students, the students that listen to classical music and the students that listen to heavy metal music. Remember, your interpretations in these problems are always about the alternative hypothesis. So what our statement here is about whether or not the pass rate for classical music students is higher than the pass rate for students that listen to heavy metal music. I want to look at a couple of kind of edge cases here. These are just sort of the weird examples where things kind of start to go wrong. So I've come up with a right-tailed hypothesis test where the null hypothesis is that there's no difference. And then when we calculated the difference in sample proportions, we ended up getting negative 10%. So right here is 0% difference. And then I'm going to come over here and put a negative 10% over here. And then the p-value is going to be everything to the right of that because this is a right-tailed hypothesis test. And something very strange is going on here. P-values are supposed to be very small percentages, like at least close to 5%, and I'm ending up with a gigantic p-value here. This p-value is certainly going to be greater than 10%. And the reason that happens is because we're checking to see if P1 is bigger than P2, and in our sample data, it is not. It actually came in smaller. So if you ever have sample results that disagree with the alternative hypothesis, then you're going to end up with a p-value that's bigger than 50%. And that's just like weird and something's wrong. The second kind of weird thing that can happen is if your evidence is so overwhelming that you get these kind of crazy z-scores and crazy p-values. I cooked up an example here that's about as extreme as you can make it. I'm checking to see if P1 is bigger than P2, and the sample proportion for group number 1 came out to be 99 out of 100, and the sample proportion for group number 2 came out to be 2 out of 100. So yeah, it's bigger. It's way bigger. 99 out of 100 is way bigger than 2 out of 100. I don't feel like you need to bring statistics into this. If you push the buttons in the calculator, you're actually going to end up with a z-score of 14. Remember, the charts really only go out to z equals positive 3 and z equals negative 3. So, if your evidence is so overwhelming, then you're going to end up with these extreme z-scores and extreme p-values that come out to be scientific notation. I mean, it's allowed, it's possible. It's just kind of a strange result that I thought was worth mentioning. I hope everyone is staying healthy and that these notes help you get through the homework. Please reach out to me on email if you have any questions, or I'm happy to meet with you on Zoom if you'd like to discuss something about your project or the homework. Okay, I'll see you guys next week.